Hello, this is Stefan again from schristoph.online. Today we'll talk about my latest blog post, the fourth in my complexity series. This one is about self-consistency. Ask a model the same question several times and takes the answer they most agree on. It turns out to be almost exactly the probability amplification trick from a randomized algorithms course. First, the old trick, randomized algorithms come in two flavors. Las Vegas, always correct, but random in time, and Monte Carlo, bounded in time, but only probably correct. Take a coin that is right a little more often than a fair coin. On its own, that is not reassuring, but run it many independent times and take the majority, and the probability the majority is wrong shrinks exponentially in the number of trials. This diagram is the theorem in one picture. If one sample is correct with probability above 1/2, drawing k independent samples and taking the majority makes the error shrink like an exponential in k. A slightly better than random procedure repeated and majority voted becomes a reliable one. That is the whole old trick. Now the new trick, chain of thought, prompting asks a model to reason step by step. And the usual decoding takes one greedy path. Self-consistency from Wang and colleagues instead samples several diverse reasoning paths at a non-zero temperature and takes the most consistent final answer, which in practice is a plurality vote. The gains are large. On arithmetic benchmarks, the paper reports jumps of well over 10 points in absolute accuracy. Line the two up and the mapping is almost embarrassingly direct. Temperature is the randomness source. The model's distribution over answers is the Monte Carlo output, each sampled chain a trial. And the plurality vote over sampled answers is the amplifier, the exact step that turns a favorable answer distribution into a more reliable aggregate. So is it really the same algorithm or just a loose analogy? It is a close instance, not an identity, and the honest divergence is the independence assumption. Self-consistency is probability amplification rediscovered in a new domain. That is not a criticism of the paper. Recognizing that a practical technique is an instance of a well-understood theorem is exactly what tells you when it will work and when it will not. And here is the catch complexity theory already flagged. Amplification comes with preconditions that are not fine print. The correct answer has to be the model's single most likely one. If a systematic bias puts more mass on a wrong answer, voting amplifies that wrong answer with the same exponential confidence, making you more confidently incorrect. And the draws have to be genuinely independent, which reused seeds or adaptive sampling break. This diagram shows both sides. A plurality vote over k samples helps only when the correct answer carries the most probability mass and the draws are independent. If a systematic bias makes a wrong answer most likely, voting amplifies it, and genuinely dependent draws break the bound. Name those conditions and the behavior of self-consistency stops being mysterious. There is also a cost lens, because amplification is not free. Every sample is a full generation, so drawing k samples means roughly k times the tokens. The error falls exponentially in k when the distribution is favorable, but the token cost rises linearly. So the marginal accuracy per extra sample shrinks fast. A handful of samples often captures most of the gain. It is a dial, not a default. So how do you run this on AWS? Self-consistency is easy on Amazon Bedrock. Send the same prompt several times at a non-zero temperature and majority vote. Because the samples are independent requests, they parallelize cleanly, and for latency-tolerant workloads, batch inference is often a better fit. The sampling is a capability the platform already gives you. The engineering is choosing k deliberately. And the reader rightly asks how this differs from the verifier in the previous post. Self-consistency is unsupervised, no checker, just agreement across samples, which makes it easy to apply but blind to a shared bias every sample carries. A verifier can catch a confidently wrong consensus that voting cannot at the cost of needing a reliable checker. Vote when no cheap, trustworthy check exists, verify when it does, and combine them on the hardest cases. This is the primary source, the self-consistency paper by Wang and colleagues. It is where the sample diverse paths and majority vote strategy comes from, along with the reported gains over greedy decoding. Reading it as an instance of the amplification theorem is exactly what tells you where its edges are. Thanks for listening. I hope this was helpful. If so, you can reach out on LinkedIn directly or head to my blog at schristoph.online. Let's keep in touch. Take care.